They see me rolling, they hating, patrolling and trying to catch me riding dirty.
This first graph that we have here is a position time graph. As you can see on the graph, you can see that my car went 6.4 meters in 5.9 seconds. The graph curves slightly towards the top because as the car was moving, it slowed down. This page shows you that I was able to find the maximum velocity and average velocity of my car. It was necessary to find both average and maximum velocity because the car was not moving at a constant rate the whole time. I found maximum velocity by taking 1/2 time times the maximum velocity, which would equal my displacement. We found average velocity by taking the displacement divided by time. As you can see on my velocity time graph, we have both my average and maximum velocity. I'm calculating that my car reached its maximum velocity at about 4.5 seconds, after which it rapidly decreased up till 5.9 seconds, where my car came to a stop. We then took my velocities and used them to calculate my acceleration. To find the acceleration when the car was increasing speed, we took the maximum velocity, subtracted it by the initial velocity, and divided the whole thing by the maximum time and the initial time. When we did that, we got that my car was accelerating at about 0.48 meters per second squared. After that, we needed to find out how much it accelerated in the negative direction after it reached its maximum velocity. To do that, we took the final velocity and subtracted it by the maximum velocity, and we took the final time and subtracted that by the maximum time. As you can see, we found that my car accelerated in a negative direction at about negative 1.54 meters per second. My graph mirrors my calculations. My car accelerated at about positive 4.8 meters per second squared for about 4.5 seconds, after which my car accelerated in the negative direction for 1.4 seconds at about negative 1.54 meters per second squared. My free body diagram shows that the gravitational force is equal to the normal force. This is because the car stays at ground level and does not move. On the other hand, you can see that the mousetrap has a much greater force than the friction. My calculations show that we were able to calculate the gravitational force on my car. The gravitational force is equal to mass times the gravitational constant. In this case, the mass of my car was 0.1 kilograms, and the gravitational constant we took was 10 meters per second squared. We were able to calculate that both the normal force on my car and the gravitational force on my car were about 1 Newton. We also know that there is a momentum force because even after the string releases the back wheel, the car continues to move forward. Here we have our energy bar diagrams. Our energy bar diagrams show us how much work was done on the wheels. We start out with no energy at all. Then we have to add work to get our kinetic energy. In this case, we don't know how much work was done, so we will have to find out the amount of kinetic energy to find out how much work was done. We can use the equation 1/2 mass times velocity squared to find out that our kinetic energy and work were 0.233 joules. Then after that, when the car is coming to a stop, work is taken out by the friction on the wheels. In this situation, we have kinetic energy minus work 2 equals 0 energy. So we can take kinetic energy again is equal to work. In this situation, we use the same formula. 1/2 mass times velocity squared is equal to work 2. Because we plug in the same numbers, we get kinetic energy, which is equal to work 2, is equal to, once again, 0.233 joules. Last but not least, we were able to calculate power. We know that the formula for power is power equals number of joules divided by time. So we have watts is equal to 0.233 joules divided by 5.9 seconds to get 0.0395 watts. When you look at the real-world connection to this MouseTrap car, you feel like there aren't many. But when you look into the physics of this car, you realize that nearly everything is related to this car. For example, the position time graph, velocity time graph, and acceleration time graph that we used for this car connect to everyday things in our life, as we are always moving. The free body diagrams that we used relate to all free objects, whether they are in motion or not, and even the kinetic energy relates to all moving things. Although the MouseTrap car may seem as if it's not related to anything, it is actually very similar to a real-life car. Both real-life cars and this mousetrap can be plotted on a position, velocity, acceleration, time graph, as well as you can draw the free body diagram for them, and they can both be expressed in terms of kinetic energy.
I'm living in that 21st century, doing something mean to it. Do it better than anybody you ever seen do it. Screams from the haters, got a nice ring to it. I guess every superhero need his